When it comes to cosmology and the Big Bang, there are, of course, many deep, many profound, and as yet unresolved problems that we are still struggling with. But certainly two of the most intriguing are surely the questions of whether our universe is the only universe, and whether reality as a whole had a beginning or could perhaps extend infinitely far into the past. And as it turns out, these two questions of whether there's one universe or many, and the question of whether time itself had a beginning, they're actually intimately connected. And I am so pleased to welcome an esteemed researcher who has been thinking deeply about these problems, and that is Will Kinney, who is a professor in the Department of Physics at the University of Buffalo SUNY. His research focuses on the physics of the very early universe, including inflationary cosmology, the cosmic microwave background, dark matter, and dark energy.
Great to see you, Brian.
Great to see you. Now, it is not part of your official bio, but I can't help but say that about 24 years ago, when I started an institute at Columbia called the Institute for Strings Cosmology and Astroparticle Physics, Will was the very first postdoc that we hired for that institute. So I like to think that you were like, the first draft pick, of the institute that we started. So it is so great to see you. And what I thought we would talk about here are the most refined approaches that we now have to cosmology, which is this so-called inflationary theory, and try to understand, A, why this theory seems to suggest there are other universes, and then B, what we can say about whether this spectrum of universes, or even one in particular, could it have a temporal quality that extends arbitrarily far back, or are we always stuck with the universe and time itself having a beginning? Those are the two questions that I thought we would focus on. So let's begin with the case for this idea of inflation and then how it gives rise to this eternal version, which is that there are many universes as opposed to one. So when we talk about inflation, how do you think of it in terms of the intellectual development surrounding the Big Bang that, of course, started in the 20th century?
Yeah, well, we know that our universe had a beginning. The one we live in.
Yeah.
It was the Big Bang. We know it was 13.8 billion years ago. We've measured that to about 10%, which is just remarkable that it's possible. And so inflation is a theory for what happened before that moment of the Big Bang. Right? So this hot, dense, early state of our universe that in the standard theory has a singularity, the math breaks down. But inflation is a way to extend beyond that point to look at an earlier epoch. And so it really is a theory for what happened before the Big Bang in our universe that we live in.
Now, does it partly depend upon language, which I know, look, English language is always, has limits in terms of truly capturing the mathematics. I know that I and many different people who talk about this stuff use slightly different language. So your description was sort of before the Big Bang. Can you also think of it as, I know Alan Guth often says, the bang in the Big Bang?
It was, yeah. So it's what created inflation explains why our universe is so big and so smooth and so close to geometrically flat. It answers all of these questions that, previous models of the Big Bang sort of left open.
And when you say left open, they basically could have just...
There was no explanation.
Yeah, just sort of say that's how it is,
It was about, you could set it as a boundary condition, right? Which is, I love the quote from Alan Turing, which is that physics is a differential equation and religion is a boundary condition. Right?
Yeah, no, we share the love of that quote, obviously. And you're right. So, when we talk about the laws of physics, they're usually framed in terms of particular kinds of equations. Differential equations is the technical term. But you always need to say, well, how does that equation
What's the input to that?
What's the input to that?
And inflation is a model that gives you the input to that, sets up the initial conditions for this, what we see in the universe. We know that the universe was hot and dense and smooth in the early. We observe this.
Yes.
Right? So this is settled science. There's lots of evidence for it. But what set that up? What created the initial conditions to allow that to happen? Inflation is by far now the leading theory.
And one way of emphasizing that point is, if someone came to you and you didn't know about inflation, and they said, I hear you talking about this big bang, everything's sort of rushing outward, what force would be pushing outward? You'd be pretty hard pressed to answer that question prior to inflation. And then inflation comes along and sort of turns gravity on its head.
Yeah, well, I mean, that's the thing, is that the inflationary epoch is really, really different than the subsequent Big Bang, right? For one thing, there is no, this hot, dense primordial soup that we see in the early universe wasn't there at all. The universe was completely empty. It was at 0 temperature, and it was expanding exponentially quickly. So it was this, instead of a Big Bang, it was sort of a cold whoosh.
And the push of that is because gravity itself can be actually repulsive.
Yeah, right. So this is the only thing, the only ingredient in the universe during inflation was the energy of empty space itself. And that is very similar to the dark energy today that is making the expansion speed up. It was sort of dark energy on steroids, much higher energy scales, much faster expansion, and it was the only thing in the universe during the inflationary epoch.
And mathematically, I mean, how does this fit into Einstein's equations that he gave us in 1915, initially showing us that space could warp and curve and so forth? I mean, do you have to stand on your head to get this to work, or does it fit?
Well, I mean, there's the lovely thing is we can steal from particle physics.
Yeah.
And the thing that we steal from particle physics is the Higgs boson, which is the Higgs field permeates all of space.
And we know that's there, right? 2012.
Right, we found the Higgs boson, we know this field exists, and it gives mass to all the particles. But it really is like an ether that extends everywhere in space.
Now, most people have heard of the Higgs particle, so you can just draw the connection between the Higgs particle
the particle
and the Higgs
is ripples in this field, but the field exists everywhere. And so we borrow that and that idea, and it turns out that the Higgs field goes through what's called a phase transition at a temperature right around the same, the energies that we're looking at that Large Hadron Collider are probing this transition. And early on, before the transition, all the particles in the Standard Model are massless, and then the Higgs field changes and gives mass to the particles. And this phase transition, it turns out that in that unbroken phase, where all the particles are massless, the Higgs field has potential energy associated with it. So it acts like a cosmological constant, or it acts like dark energy. Empty space, this field that permeates all of space, has an energy associated with it. And that can drive accelerated expansion.
So there is a connection to observation, you're saying. So we do know of an actual field
that works this way.
That works this way, that's filling space, and it contributes in energy to space. And the impact of that is it gives ordinary particles the masses that they do. As they try to plow through this field, they acquire mass from that interaction.
Yeah, and it was pointed out in the 1970s, well before Alan Guth came up with inflation in particular, that this Higgs field would source something that looked like a cosmological constant. So this was something they realized before.
That was known before Alan Guth
1976, Andre Linde.
And Stravinsky, I guess.
It was Linde, and also an American physicist who's less well known named Joe Dreitlein, who was at the University of Colorado, wrote a paper
I don't know
in 1976.
Wow.
Yeah.
Amazing. And they just didn't push this idea.
They didn't quite close the gap and really realize that it could solve all these other cosmological problems, like why the universe is so flat and why it's so smooth and things like that. But they realized that it acted like a cosmological constant.
So the idea then is not to literally use the Higgs field, but to model the idea.
Right. So this would be something like the Higgs field, except at much higher energy, but it would have similar characteristics. It would go through a phase transition where the vacuum had energy, and then it's the energy in that vacuum that decays and heats up the universe and creates that hot primordial soup in the early Big Bang.
So an analogy to think about the energy in space that people often use, and it's not perfect, but it's pretty good, is a very simple one of just having like a ball on a hill, and it has more potential energy when it's up on the hill, and then it rolls off. Is that a reasonable way of modeling?
Yeah, I mean, or you can think of it if you have balance a pencil on a tip, and it falls over, right? When the pencil's sitting upright, it has potential energy. And then
And it
as it
releases
falls
it.
over, it releases that energy
Yep.
into kinetic energy. And that's
Yep.
very similar to what happens to one of these Higgs-like fields
Yeah.
that goes through a phase transition.
So if that yellow ball, if we go back to the ball analogy, so when it's higher up on the hill, I mean, tell us how to interpret this.
So the hill is basically just a plot of the energy of a system as a function of its state. In the case of a pencil, it's the energy as a function of angle. Any phase transition, even like a ferromagnet or something like that, you can do a plot of this energy as a function of sort of the state of the system. And so what you have there in this picture is that ball is trapped in a little what's called a metastable equilibrium. And so that potential energy then this is, remember, the energy of a field that's extending through all of space.
So that looks like it's one point. But
yeah, but it's actually, it's just a plot of the energy of the space. And so that when it's up there, that potential energy is stable, and it will drive this exponential expansion.
Yeah, so when the energy is in a configuration modeled by that ball, that gives rise to, as you say, this energy that drives this repulsive gravity, and that idea is what is the bang, pushing everything apart. Right. But then if we go back to the ball on the hill, ultimately that rapid expansion has to stop, right? So this guy...
Right, because the universe is not cold and empty now,
yep.
right?
And so this guy ultimately, in this early version of the theory, sort of does a quantum tunneling move and is able to roll down.
That was how Alan Guth's original theory of inflation was constructed, and he immediately realized that it didn't work.
And in the paper, the last couple paragraphs...
He actually says so.
He says so,
That's right. So he realized that what happens is that ball is too sticky up there. It gets stuck up there, and it doesn't transition downward fast enough. And so you had to modify this in a way to make that transition happen in a way that would result in a universe that looks like ours.
And people did so, right? So they basically changed the shape of this hill, this potential energy curve, and found what here?
So when the ball is up on that flat plateau, it's a phase called slow roll is the technical term for it, because the expansion creates drag and slows that ball down. And so it rolls very, very slowly, which means you get a lot of inflation, right? You need to have the universe increase in size, right? Our observable universe today during inflation was about the size of a grapefruit. And so you have to take something about the size of a grapefruit and expand it about 10 to the 26th power.
And in what duration of time?
In 10 to the minus 35th seconds or so. I mean, an incredibly small amount of time.
Right.
And so, but it has to go on for long enough to create at least that much expansion. It can go on for longer, and when we talk about eternal inflation, we'll talk about that, right? And so then when it rolls down into that little basin at the minimum, all that energy that the energy of that space gets converted into standard model particles, and it heats the universe up.
So as the ball kind of does this, as it gets down to the bottom,
as it's wiggling back and forth,
it's firing out
particles
from that energy. That slows down its motion, and it's converted into the stuff that ultimately makes
all of that, the quarks and the protons and neutrons and all the particles that make, and the dark matter, whatever it is, right? You know, all of it gets created in that phase of reheating at the end of inflation, which is kind of a misnomer because it was never heated.
It was never heated in the first place. So this is actually a beautiful idea, right? So you're saying this very simple starting point of space just being uniformly filled with this inflaton field, if we use the language of the subject.
And we don't know what it is.
And we don't know what it is, though.
So it's a placeholder for some physics that we don't fully understand.
So do you hold out the possibility that this is all just a nice encapsulation of the basic processes that had to happen, but maybe this isn't the right detailed explanation of what drove the inflationary phase?
It could. It is the way a mathematician or a physicist would say it is. This is an order parameter. It's just a label that we put on the state of this thing. But what the nature of the underlying physical nature of that thing is entirely unknown.
And so, what really gives us confidence that this idea of inflation is? I mean, are there observations that you hang your hat on when you think about?
The remarkable thing is that there are, right? So this looks like philosophy, right? We can say, oh, this
Not
explains all
to
this.
say anything bad about philosophers.
We like philosophers,
right?
yeah. But it actually makes concrete predictions because when you add quantum mechanics to this, magic happens, right? So you come up with this model that explains the big properties of the universe, like flatness and smoothness and stuff. But then when you add quantum mechanics to it, because of quantum uncertainty, it makes little fluctuations, little ripples. And those ripples get stretched out to enormous distances by the expanding universe. And those are the things that seed structure in the universe.
Yep.
So what we're seeing here is a picture of the cosmic microwave background. This is like literally a photograph of the universe when it was 380,000 years old. And those little hot and cold spots are regions that are a little more dense or a little less dense than their surroundings. And these then are the seeds of all the galaxies and clusters and structure in the universe. Those little overdense spots collapse under their own gravity over time and form stars and galaxies and so on. And the pattern of those hot and cold spots, or those overdense and underdense regions, inflation makes a very specific prediction about how they should look. And the cosmic microwave background that we see here that was measured by WMAP satellite and the Planck satellite, actually now we have an extremely precise measurement of these perturbations, and they match exactly what you would expect from inflation.
So on this curve here, the solid line is the mathematics.
Is the model. And the yellow points are the dots. And there's a lot of structure in here, right? There's all these bumps and wiggles, and it nails it.
Yeah, I mean, it's breathtaking, the agreement between the two. So this esoteric sounding idea certainly is comporting with things that we can actually observe.
And it makes very specific specific predictions that are hard to reproduce any other way.
So let me ask you one question along those lines, which is not the main focus of what we're talking about here per se, but there are some other models that have been put forward. In fact, toward the end, we'll come back to one of them, these cyclic models.
That's right.
Do you find them compelling alternatives to?
The idea is, at least they're sold as they solve problems that inflation has. And I don't find them to be a compelling solution, and I find that they have all of the problems that inflation has and add a few more into them. So I personally, my own take on it is that they're not as parsimonious or as elegant as inflation is.
Now, you mentioned quantum mechanics as being this beautiful overlay of the inflationary theory that gives rise to the ripples, that gives rise to the temperature variations, the microwave background gives rise to the seeds for the formation of structure. So it's a beautiful chain of events that goes from the Big Bang to us. But as we mentioned early on, inflation has to end, at least in our region, but it's not so easy to do that, especially when you take quantum mechanics into account, because if we look at just sort of a part of the hill, right, quantum mechanics can drive the energy in that field up, it can drive it down. And so what does this entail for reality as we know it if that field is not going to go to like zero everywhere because of these undulations?
Yeah, that's the wild thing. So you have this theory that explains all sorts of stuff, makes really non-trivial predictions that we've gone out and tested, and those predictions turn out to have been correct, right? Good, solid science. But then when you actually look at the consequences of this, is almost any model of inflation that you write down, that those quantum fluctuations very early on are going to be so big that they're actually going to drive the ball up the hill rather than down it. And this is called a phase of quantum diffusion, where the quantum evolution dominates over the classical rolling down the hill. And in that phase, what happens is that inflation might end locally, right? It will roll down the hill, like in where we live.
Yeah.
But in other places, it will actually have bumped up the hill, and inflation will still be going on. So immediately, as a consequence of this theory, as soon as you work out what it means on a larger scale, what you find is that there wasn't just one place where this field decayed and created a Big Bang, but there are multiple places. You end up with a multiverse for free, almost inevitably.
So if we take a look, I think we have a nice little multiple Big Bangs. So that could be like inflation in our region that maybe then dies down.
And it's happening now. And in between those, all of those little bubbles Inside each one of those bubbles is an infinite universe like our own,
Yep.
and in between them, the space is still expanding exponentially quickly, and they're being pushed apart from each other faster than light. And this process goes on indefinitely. So instead of getting one universe, you get an infinite number of them toward the future.
So this is sort of a crazy Copernican revolution,
Yeah,
right?
right. Is that our universe isn't even unique, right?
Right.
So this is Copernicus's idea writ large, that he realized that the Earth was not unique and the Sun was not unique, and it was Giordano Bruno who took that to its logical conclusion.
And
said
he
there
paid
must
the
be-
price for it.
Yes, he did. He was burned at the stake at Campo di Fiore in 1600,
Yeah.
and part of the reason was he preached this doctrine of an infinity of worlds. Now this is taking Bruno's idea of an infinity of worlds and turning it into an infinity of
Infinity of infinities, right?
Yeah, exactly.
Yeah. And so there is some criticism that inflation gets for this quality. And I wonder how you come down on it, which is if there are these infinity of universes, and when you look at the math, the detailed properties within those universes, I think we just sort of have some kind of, schematic sketch, sort of an artist's rendition of these other universes, but the details inside those other universes will generally vary. And if you have an infinite variation of universes out there, the critics say, any observation that you ever make can be accommodated in one of those universes, so how is it ever falsifiable?
Yeah, it lies at sort of the gray area between science and non-science, right? And because it's an inevitable consequence of something we can test, but we can never actually go out and observe those other universes. So we don't really know, and we can't know, whether the laws of physics in these other universes are different from ours or the same as ours, right? And certainly that depends on the theoretical underpinning that you use. But it's not testable. But it is nonetheless a consequence of something that we can test. So
does that trouble you?
I've come to terms with it. I had a hard time accepting it for a long time, but finally when I started realizing that there's just no way out of this, then you just have to learn to live with it.
I think I'm sort of in the same boat, I have to say, but it is sort of a strange place to be. But given that, I now want to turn to this question of whether the cosmos began, and that's really meant in the largest sense. Whether there's a conception of going further back in time, and you can just go arbitrarily far back, or no matter what, do you sort of encounter a beginning?
Right, so the beginning of our universe really is the formation of one of those bubbles, right? What we call the Big Bang is just our particular bubble forming in this picture. And so, but now these bubbles live in this bigger arena, and you can ask the question now, did that have a beginning, right? We know that our bubbles had a beginning. But whether or not this larger structure that contains these multiple universes had a beginning is a really interesting question, and one that I've been working on a lot lately.
And you, I gather, are following somewhat in the footsteps of this well-known paper of Boord, Guth, and Vilenkin. So tell us what these guys
so this
found.
was about 20 years ago. And these three authors gave a very elegant mathematical proof that as long as the universe was on average expanding, then it had to have a beginning, inevitably as a result of the laws of general relativity.
So the only assumption is sort of on average that space
that the universe is getting bigger and not getting smaller.
Smaller.
And that's
all
the
you
only
need.
ingredient. And that and Einstein's theory of relativity.
This is a tough theorem to explain in general terms, but can we just give it a shot? I think you're familiar with the visuals that we're trying to use here. So what are we seeing here?
Well, what you see is any particle that's moving through the universe, right? Because of the expansion of the universe, as the universe gets bigger and bigger, there's a thing called expansion drag. It actually acts like a friction on a moving body. And so as any body that is freely moving in the universe will gradually slow down and come to rest.
So can we sort of see this here? So this is the speed of the particle, say, when the universe has one size. If we now, say, go on to the next size, where the grid lines are farther apart, you see that it's crossing the grid lines and its speed is slower. Tick, tick. And if the grid lines are even farther apart from
And it goes
expansion,
slower.
you go tick, tick, even slower and slower.
And so everything comes to rest in an expanding.
In the future.
Right. Which it violates conservation of energy because it.
But we're fine with that when it comes to the universe as a whole.
Exactly.
Right?
And so this is a general property of any freely moving body in an expanding space-time. So
then,
now if you turn the clock backwards.
Exactly.
Right? If we have some object that is moving at some speed relative to the expanding universe, if we look at where it must have been earlier on in the universe, it would have been moving faster. And if we look earlier still, it would have been moving faster and faster.
So we sort of try to schematically show it going faster and faster and faster, crossing these grid lines that are ever closer together.
Right. And if you take that, so now you wanted to say, can we take this back infinitely far? This is a question that mathematicians call geodesic completeness. But the idea is, if we take the path of that particle infinitely far back, from the point of view of that particle, is that a finite amount of time or an infinite amount of time? And the relevant physics here is Einstein's time dilation, right? As we go back in time, and we'll look at this particle very early in the universe, it was going closer and closer and closer to the speed of light. And if we go infinitely far back, it will become arbitrarily close to the speed of light. And essentially, the clock that particle carries along with it, its perceived time, called the proper time, its clock will stop. And the mathematics of this is wild because it takes what an observer at rest would see as an infinite amount of time in the past, this moving observer will actually see as finite.
No time at all.
Because of time dilation.
And so this tells us that if you were to follow the trajectory, the so-called world line of this particle ever farther back in time, you would find that trajectory actually comes.
It's a boundary.
It's a boundary.
In finite time. And the only requirement, the only ingredient that you need to show this is that the universe is expanding. And
so this seems to suggest that no matter what, you encounter a beginning, even in this multiverse of an infinity of universes.
It's infinite to the future, but not the past.
And so what is that like? Isn't that strange?
Yeah. Well, interestingly, Einstein's theory of gravity contains within it its own undoing, the existence of these singularities. And another example of it is the singularities at the centers of black holes.
Black holes, sure.
Right, so you
That's
can
also
show
where time comes to an end.
Exactly. So the world lines of particles falling into a black hole hit this mathematical point of infinity in a finite amount of time.
Now that's their future.
That's called the future singularity.
Yeah.
The singularity in these inflationary cosmologies is called a past singularity.
Yeah.
So the universe arises out of a point where all of our mathematics breaks down, and it's just an inevitable consequence of Einstein's theory of gravity and the fact that the universe is expanding.
Yep.
That's it. So it seems that pretty much no matter what you do, even if you have this multiverse that's expanding infinitely into the future, creating an infinite number of universes, if you start at any finite point and look backward, there's always some beginning. Now, it's not, that beginning wasn't, the beginning of our universe was 13.8 billion years ago. This could be vastly larger, right? Incredible, unimaginable.
And it can differ for different particles, right? It's not as though every trajectory ends at the same beginning. It's just that each of them ends.
And so, but the universe is vastly older than 13.8 billion years, but still finite.
Now, I don't want to spend a whole lot of time on it, but I've certainly caught wind of the chatter that theologians have sort of jumped on this idea. I mean, have you encountered any?
Yeah, actually, we wrote a paper on the BGV theorem recently, and it was there were a number of creationists who made.
So you're making them very happy?
Yeah, they loved it. Yeah.
Right. and
because the universe had a beginning. If you think about it, really, the idea that the universe had a beginning is really one of the most consequential scientific ideas of the 20th century and into the 21st, right? The universe of Newton and Descartes, space and time were this infinite arena in which physics took place, and they were eternal and unchanging. And it was Einstein and Einstein's theory of gravity and the discovery of the expansion of the universe undid all of that, created this idea that the universe had a beginning. And it is persistent. We can't get rid of it. It's very hard to write down theories where the universe didn't have a beginning.
In fact, another approach, and we briefly mentioned it, but let's just step through its history a little bit, that people introduced to try to get away from a beginning was this idea of cyclicity.
Sure.
That maybe the universe goes cycle after cycle, and maybe an infinite number of cycles was the idea. I think the version of this that I know best, in terms of historically speaking, was that from Richard Tolman, who I guess was thinking about this in the 1930s or something like that. But quickly, it was realized, and I think it was by Tolman himself, that if you followed the cycles over and over again, and you sort of looked at the second law of thermodynamics as entropy has to increase over time, then when you look, and I think we can sort of see it here, if you look at the duration of these cycles going back through time, then the duration of each previous cycle was shorter, 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 so you'd still hit a beginning, even in this approach. But you've pushed now the Born-Guth-Vilenkin theorem to another version of cyclic cosmology, I guess coming from Paul Steinhardt and collaborators, where in principle those researchers are suggesting that it could go infinitely far back. There could be infinitely many cycles in their approach, but you find that there'd still be a beginning, right?
Anna Eosh and Paul Steinhardt came up with a very clever solution to Tolman's problem, right? Yeah. So the idea is, Tolman showed in this very influential paper in 1931 that as long as entropy increased, you couldn't have a truly cyclic universe because each cycle would have more entropy than the last.
Precisely.
And an example of this, an extreme example of this, is forming black holes. As soon as you make black holes, when the universe crunches back down again, you don't have a nice smooth Big Bang anymore. You have a mess.
Yep.
Right? And so you got to get rid of the entropy. And they came up with a very elegant way to do that, which is that they said that the expansion rate is cyclic rather than the size of the universe itself, right? So between each cycle, the universe gets a lot bigger. They incorporate a phase of inflation
and
into
they
it.
basically push the entropy out.
All the entropy gets diluted.
Yeah.
And then you collapse again, and the next cycle gets even bigger and dilutes the entropy from the last cycle, and this goes on. And their argument was that this could go on eternally into the past. And so what my graduate student Nina Stein and I looked at was applying the Born-Guth-Vilenkin theorem not to inflation but to the cyclic cosmology, and showed that for the same reason that inflation has to have a beginning, right, that because of the fact that the universe is on average expanding, in this case the universe is still on average expanding from one cycle to the next. And so for the same reason that inflation has this geodesic incompleteness problem, then this model as well. And so there are also observers in the cyclic model that will see a boundary in their past, inevitably. And so as soon as you solve Tolman's entropy problem by diluting that entropy with expansion, you run afoul of the BGV theorem, and then you find that they had to be past finite because of that.
And then you're stuck
with... So you're on the horns of a dilemma.
So you have religion as a boundary condition again, you know, no matter what.
So their model doesn't work.
Right.
It does not create a
And what do they, have you spoken with them?
As far as I know, they've entirely ignored our paper, so I'll have to ask them.
Inconvenient truths, I guess. So the final topic here in the last couple minutes, sort of maybe poetically thinking about sort of the future of the beginning, if you will. We still lack a quantum theory of gravity, which I think ultimately you're gonna need to knit things together more fully. You've certainly made reference, and the field as a whole certainly has incorporated elements of quantum mechanics into our theorizing, and you know, the ripples in the microwave background rate. So there are ways in which these ideas can coalesce, but the early universe is so extreme that presumably if we want to get away from things like, you know, the singularities that beset all these theories, you're going to have a quantum theory of gravity. Do you see that as where these answers will come from?
Probably, I would think. You know, so that these calculations show that there has to be some sort of a boundary, but they don't tell you what the nature of that boundary is. They tell you it's out there, but it doesn't tell you anything about what it's like. One of the problems is that if inflation is correct, inflation acts like a giant eraser. Whatever those boundary conditions were, whatever that weird physics that happened is on this initial surface, this point of religion is washed out by the inflationary expansion and is inaccessible to us. So this is something where theory is going to have to come up with at least speculative answers to this question. And I think most of us think that the answer, you know, what the initial state of inflation was, is going to be some sort of quantum gravitational state where space and time themselves are quantum mechanical, And we just don't have a theory that does that yet.
Right.
So it's very difficult to.
But could you imagine, for instance, the Turing quote ultimately really, I know we're using it poetically and somewhat facetiously, referring to this boundary condition as religion, but the idea that physics is about two things, the laws and the initial data, is pretty widespread in our thinking about things. Can you imagine a more fundamental theory where those are so blended together that we don't bifurcate the way we think about the laws and the initial conditions?
Yeah, that's tough, right? Because as physicists, this is what we do: is we derive the way things evolve from a particular. If you give me an initial state, I can give you physical laws that will tell you what will happen to it later. So I think it's going to require some sort of real revolution in how we conceptualize physical law, in that whatever this initial boundary state was, is not going to have such a clear distinction between cause and effect, right?
Yeah.
So it's going to require a revision of what we even think of as causality. And quantum gravity is almost certainly going to have those properties, right? I think you would agree with that.
I do agree with that. And one final, unfair speculative question is, we use this vocabulary of space and time in everything that we have spoken about here today. Of course, a very generalized version of space that could embrace not just our space, but the space that contains these other expanding realms coming from the eternal inflation. Do you see evidence for there ultimately being a language in which we don't use space and time at all in our description of the extreme state of the early universe? Rather, there's some other language, and then we find space and time emerging only in certain environments.
Well, that's the hope, isn't it? I mean, nobody's really managed to come up with a convincing way to do it. People have made various attempts. There's string theory. There's also loop quantum gravity, which I think is more directly sort of the kind of theory that you're talking about, where in fact space and time are emergent properties of these connected networks of nodes and things like that, right? Lots of smart people have attacked this problem, and none of them have really been successful at it in any meaningful way, as far as I've seen.
Well, we can still hope.
Yeah. Well, that's your job. I'm just a silly cosmologist.
Yeah. Well, much more than a silly cosmologist. Thank you so much for this great conversation.
Thanks for inviting me.
Thank you. Appreciate it.